Hello, God bless you, and thank you for watching my videos. Please like and subscribe to my channel, and if so moved, contribute to sponsor my research and ongoing scholarship via the PayPal link and or whatever other means I may provide in the future. Part 1 covered integer-valued polynomials, also known as numerical polynomials, and I was going to do this Part 2 on Vandermon's identity, but I kind of left the end of Part 1 with some hand-wavy stuff that I feel compelled to detail now. So Part 2 here is just going to focus a little more closely on Polya's formula for his coefficients versus Gregory-Newton, which is really the same thing. And then we'll cover Vandermon's identity in Part 3. In Part 1, we looked at integer-valued polynomials. These are all polynomials f of x for which every value at integer arguments is itself an integer, and observed that this does not necessarily mean that all of the coefficients in the canonical expression of the polynomial are going to be integers. So it's a broader class than just integer coefficients than polynomials with integer coefficients. And then we looked at this paper by Cahill and Chabert and looked at the Gregory-Newton forward difference formula compared to Polya's formula, and kind of observing or concluding that they're kind of basically the same thing. Maybe that wasn't quite fair. Polya's is basically a rearrangement of it. When you look at it in terms of differences on this basically Cartesian sort of construction of Pascal's triangle here. Also called numerical polynomials, they are a larger set than polynomials that have integer coefficients in the canonical representation of coefficients multiplied by each power and summed together. If you have integer coefficients and integer arguments, you are always going to have an integer value at all integer arguments x of f of x. But in addition to those, the numerical polynomials include polynomials where every value at integer arguments is an integer, but the coefficients are not all integers. And that's a bigger set of polynomials then. And many works introducing the subject will give the polynomials that yield the binomial coefficients as prime examples of something that is a numerical polynomial but does not have integer coefficients across the board. Here, 1/2 t squared plus 1/2 t is the polynomial that gives the choose 2 binomials. In other words, this sequence from negative infinity to infinity, where, in order to specify a specific polynomial, we need to observe this sequence at one point. We need to determine what is f0, because you could assign f0 to be any number along that line and you have a different polynomial as far as modern mathematics is concerned. Call me a heretic, but I like to look at that infinite sequence as the function, and the coefficients of whatever polynomial you derive from it are just specifying what is the observation point, what is the f0. Regardless, the only point I want to make here is that if we have rational coefficients but non-integer rational coefficients, translating the index around, integer index by integer translations, is not going to ever change the fact that all of the coefficients are non-integer rationals. I also want to point out that as we change that point of observation, say by translating in units of 1, that the coefficient sequences in the columns here are going to themselves form polynomials from degree d on down to degree 0. Here, the constant term follows a second degree polynomial equation, in fact the same one, and the middle term is a degree 1 arithmetic progression, and that's corresponding to the x to the 1 power term. And of course the x to the 2 power term has a constant coefficient of 1, aka a 0 degree or constant polynomial. So our singular point of observation then becomes the index for d different polynomials expressed in the coefficients. Actually d plus 1 polynomials, where the degree of the polynomial or sequence of coefficients in any given column here, corresponding to a degree of, or a power of x, the power of x degree and the degree of the sequence thus formed are always going to sum to the degree of the polynomial. So they're homogeneous in that sense. Homogeneous in the sense that the degrees of the component parts of each term add up to a constant degree, d, of the function. Here's an example for the choose 3 binomials, which has a third degree polynomial function that describes it. So as we choose our observation point, our constant term forms a sequence which is a third degree polynomial. And in fact, the very same polynomial as our original. And then the 3 columns to the right of that, beginning with the t degree 1t term, well, that's 1, so 3 minus 1 is 2. So those coefficients, that coefficient sequence is going to be following a quadratic equation, b of degree 2. So 2 plus 1 equals 3. And then in the third column, our coefficient sequence is a degree 1 polynomial, an arithmetic progression for the t squared term. So 2 plus 1 equals 3. And then, of course, the same thing in the fourth column as we had before. It's always going to be third degree plus a 0 degree sequence of coefficients. And I'm kind of sort of hoping that this gives you an intuition, a sense of why Pascal's triangle constructed in a Cartesian square quadrant here, like on the upper left here, why this is an intuitive basis for examining Polya's formula and the Gregory-Newton forward difference, and then we're going to get into showing how it's pretty much the same as van der Waals' identity. Now I say pretty much the same, but I mean there are differences. Polya did not copy Gregory-Newton on this construction. He's doing the same thing, just in a different order. In other words, applying Polya's formula. Basically, on the first one here, we have C0, and there's no summation term, so C0 equals F0. And then C1, following the recurrence, gives us F1 minus C0 times 1 choose 0, or expressed in terms of values of the original function, F1 minus F0. And we can see when we do C2, we eventually get that expressed in terms of the first 3 values of the function. And we have coefficients 1, negative 2, 1 applied to F2, F1, F0. So you can imagine that if we go to C3, that's going to be f of 3 minus 3 times f of 2 plus 3 times f of 1 minus f of 0. So each of the Polya coefficients, C0, C1, C2, etc., are computed by applying these coefficients to consecutive values of the function, in this case in descending order. And what are these coefficients? Well, they're just the rows of Pascal's triangle looked at in the normal way, except that the values alternate the sign, plus minus, plus minus. So we can apply each of these rows of Pascal's triangle in the alternating form to values on the directly to the sequence of the polynomial, and each subsequent one is going to give us a subsequent Polya coefficient which is the diagonal of that construction, aka this Cartesian representation of Pascal's triangle. But the sequence on the top here is ultimately just a fourth degree polynomial, so we can take any fourth degree polynomial sequence and consider it to be our top row of a construction like this. And what Polya showed is that it's just a linear combination of basically copies of this Pascal's triangle written out this way, and that no matter what your function is, if you want that say the third Polya coefficient, C2, well, that's 2 rows down, and it's this diagonal value 6 here. So we just need this 1 minus 2 plus 1 applied to 3 consecutive values of the fourth degree polynomial that we're dealing with. So here, 1 minus 2 times 5, that's negative 9, plus 1 times 15 gives us a positive 6. So you can see that the 1 minus 2, 1 coefficient applied on that edge then goes down to this 6 to the lower corner here. And it's going to work like that everywhere, whether we're dealing with the plain Pascal's triangle written out this way or a function written out this way, where then the functions below that function are very easy to derive by the same process. And what is that process? Well, it's the same thing, the same recursion that you would use to generate Pascal's triangle, except you're applying it to a function which is just a linear combination of Pascal triangles, so you can do them all at once. You're lumping them together. So here, this look at this here. 1 times 20 is 20, minus 2 times 35 is 20 minus 70 is negative 50, plus 1 times 56 gives us positive 6, which is the lower diagonal value here on this. It's all relative no matter where you place this overlay. Let's look at 21, 28, 36. 21 minus 2 times 28 is negative 35, plus 1 times 36 gives us a positive 1. This is just Polya's formula applied to a quadratic sequence to give us a C2 relative to it, a C2 coefficient that has 0 degree because the degree of the polynomial is 2, and that happens to be 1, the constant in this case. So Gregory-Newton's forward difference treatment just is really essentially computing C1 and then resetting the function being operated on to the next degree down. So Polya's formula is just a demonstration of what it takes to do the same job without resetting the formula. I should say without resetting the polynomial that the formula is working on. And it is in this sense that Polya's is basically a reformulation of reordering or done differently of Gregory-Newton's. Now let's look at how polynomials are actually computed using Polya's coefficients, or the diagonal here. In part 2 of this series, we're going to see that both of these are also pretty much equivalent to Vandermon's identity. So please check that out, and in the meantime, like this video, subscribe to my channel if you have not already, and please click on the PayPal link or whatever other means I may provide in the future and contribute to my further research and scholarship. Thank you, and God bless you.